Reflection of waves. An everyday example of reflection of sound waves from a rigid boundary is the phenomena of echo. If the boundary is not completely rigid or is an interface between two different elastic media, the effect of boundary conditions on an incident pulse or wave is somewhat complicated. A part of the wave is reflected and a part of wave is transmitted into the second medium. And if the wave is incident obliquely on the boundary between two different media, the transmitted wave is called refracted wave. The incident and refracted waves obey Snell's law of refraction, and the incident and reflected waves usually obey laws of reflection. And to illustrate the reflection of waves at a boundary, consider two situations. First one, a string is fixed to a rigid wall at its left end, as shown in figure A. And the second one, the left end of the string is tied to a ring which slides up and down without any friction on a rod, as shown in figure B. A pulse is allowed to propagate in both the strings. The pulse on reaching the left end gets reflected. The state of disturbance in the string at various times is shown in the figure. In figure A, the string is fixed to the wall at its left end, and when the pulse arrives at that end, it exerts an upward force on the wall, and by Newton's third law there will be opposite reaction. This second force generates a pulse at the spot, which travels back along the string in the direction opposite to that of the incident pulse. In a reflection of this kind, there must be no displacement at the support as the string is fixed there. The reflected and incident pulses must have opposite signs so as to cancel each other at that point. Thus, in case of traveling wave, the reflection at a rigid boundary will take place with a phase reversal or with a phase difference of 180 degree, as shown. In this figure, the string is fastened to a ring which slides without friction on the rod. And in this case, when the pulse arrives at the left end, the ring moves up the rod. As the ring moves, it pulls on the string, stretching the string and producing a reflected pulse with the same sign and amplitude as the incident pulse. Thus, in such a reflection, the incident and reflected pulses reinforce each other, creating the maximum displacement at the end of the string. Thus, the reflection is without any additional phase shift, and in this case, traveling wave, the reflection at an open boundary will take place without any phase change. A traveling wave at a rigid boundary or a closed end is reflected with a phase reversal, but the reflection at an open boundary takes place without any phase change. Mathematically, yi will be equals to a sine kx minus omega t. Then the reflection at rigid boundary denoted by yr will be equals to a sine kx plus omega t plus pi, or you can say minus a sine kx plus omega t, but in case of open boundary it will be simply a sine kx plus omega t. Standing waves and normal modes. Consider a system which is bounded at both the ends, such as a straight string fixed at the ends or an air column of finite length. In such a system, suppose we send a continuous sinusoidal wave of certain frequency towards right. And when the wave reaches the right end, it gets reflected and begins to travel back. And the left going wave then overlaps the wave traveling to the right. And when the left going wave reaches the left end, it gets reflected again. And so on. and there will be overlapping of the waves, and this process will continue. The equations of the waves traveling along the positive direction of x-axis will be a sine kx minus omega t, and towards the negative direction of x-axis will be a sine kx plus omega t. And by using the superposition principle and by using this trigonometry formula, by combining y1 and y2, you will get 2a sine kx cos omega t, where 2a sine kx is the net amplitude of the oscillation of the element of the string located at the position x. This figure represents the formation of the standing waves given by equation 10. Standing wave, a wave in which the waveform doesn't move. The points where the amplitude is 0 will be called as node, and the value of kx will be equals to n pi, where the value of n starts from 0, 1, 2, 3 and so on. By putting the value of k as 2 pi by lambda, you can find out the value of x, and that will be the n times lambda by 2. And for maximum amplitude, the sine kx must be equals to 1, means the value of kx will be equals to n plus half into pi. And again, by putting the value of k as 2 pi by lambda, you can find out the value of x. And such points are known as antinodes, where the position of maximum amplitude. For a stretched string of length L, fixed at both ends, the two ends of the string have to be nodes. One at the position x is equals to 0 and at other x is equals to L. And you know that lambda is equals to 2L by n. So we can find out the frequency by using V is equals to nu lambda. And you can find out the value of nu as NB by 2L. And this will give you the set of frequencies called the natural frequencies or modes of oscillations of the system. The oscillation mode with the lowest frequency is called fundamental mode or the first harmonic. Then for n is equals to 2, it will be second harmonic and so on. And similarly for the frequencies. Some of the frequencies for the fundamental or the first harmonic is shown in figure A, for second harmonic in figure B and so on. According to the principle of superposition, a stretched string tied at the both ends can vibrate simultaneously in more than one modes. Which mode is strongly excited depends upon where the string is plucked or bowed. Musical instruments like sitar, violin are designed on this principle. The modes of vibration of a system closed at one end with the other end being free. The air columns such as glass tubes partially filled with water provide examples of such systems. And in these, the length of the air column can be adjusted by changing the water level in the tube. The pressure changes here are the largest, since when the compressional part is reflected, the pressure increase is doubled, and when the rarefaction is reflected, the decrease in pressure is doubled. On the other hand, at the open end, there is maximum displacement and minimum pressure changes. So, by following the same conditions as we have discussed earlier, you can find out that if the length of the air column is L, then at open end x is equals to L, there will be antinode. And the value of L will be equals to n plus half lambda by 2. And the modes which satisfy the condition lambda is equals to 2L upon n plus half, or you can find out the frequency again by using V is equals to nu lambda formula given by equation 17th. This figure shows the normal modes in an air column with the open end shown. The figure A represents the first harmonic, then B represents third harmonic, and so on. The fundamental frequency is V up by 4L, and the higher frequencies are odd harmonics. In case of pipe open at both ends, there will be antinodes at both the ends and all the harmonics will be generated. You can derive the formula by following the same steps. This figure represents the standing waves in an open pipe, and you can see that at both the free ends there are antinodes.